Hello dear students, welcome to the lecture series on microelectronics. This is lecture number 14, Introduction to MOS Amplifier with Active Loads. Now in the previous lecture we tried to cover the current mirrors and current sources concepts, and we also saw the impact of Miller's theorem. Now in today's lecture we are going to see what exactly we mean by the active load, and we will also see by using an active load what will be the benefit that can be obtained in terms of gain for any MOS amplifier. Now, basically, till date, we used the resistive load as one of the main load for any MOS amplification. But building a resistive load or resistor itself on an IC on an integrated circuit becomes a tedious task because of the space problem or because of the area problem. So, hence, we need to mimic the operation of resistor and replace that resistor with something that also allows constant current to flow through it. Now, one of the straightforward element that comes to our mind is why not we replace the resistor with a current source itself. Now, again, by using a current source that typically we use in the laboratories, we cannot be using that. Of course, we can use those things when we will be doing the discrete experiments. When I do the experiment in the labs, possibly I can be using a discrete current source. But if I want to build the entire setup of amplifier in an IC, then possibly the discrete current sources would also fail. Now, hence, the only option left out is to build the current sources using MOSFETs, because MOSFETs being very tiny elements, and I can utilize the MOSFETs in building the so-called current sources, and by using those current sources, I can be using them as a load. So basically, the agenda is the same thing. I'll be using MOSFETs to build the current sources and use that current source as a load. And once student understand all these concepts, he'll be in a position to understand the exact difference between the active loads and the passive loads when it comes to the MOS amplifiers.
Dear students, we know that there are different kinds of loads that can be used whenever we talk about amplifiers. Now, two common types or distinguished loads that we often talk is active load and passive load. Now, basically, active loads are those loads which are made up of active elements like current source, voltage source, etc. Now, passive loads are those loads which are made up of passive devices or passive elements like RLC. Now, in most of the cases, whatever the amplifier circuits that we have learnt, in almost all those cases, the load whatever we have used are our passive loads. Now, the common load that we have been repeatedly using is the resistor. But when we try to build the same amplifier in the form of integrated circuit, there building a resistor will be a big hurdle, because normally resistors take up far too much space on integrated substrates. Therefore, we need to make a resistor out of a transistor. Now the question is, how can we do that? After all, resistor is a two-terminal device, whereas a transistor is a three-terminal device. Now definitely we can make a two-terminal device from a MOSFET by connecting the gate and the drain as shown in this figure. By connecting the drain and the gate, we ensure that the MOSFET is pushed into saturation region and a constant current is flowing, which in turn makes the property of a resistor similar to that of a MOSFET, because we know that in a resistor the current will be constantly flowing, and by connecting the drain and gate terminal like this, we are ensuring that device is in saturation, which in turn means the current will be flowing constantly. Now again the question is, how does this enhancement load resemble a resistor? Like I told, if I consider the IV curve here, since the gate is tied to the drain, which means the VG is equal to VD, and then that also satisfies the condition VDS greater than or equal to VGS minus VT always. Remember here the VGS is always, or VDS is always greater than or equal to VGS minus VT, so that makes the transistor to remain in the saturation region, and that in turn ensures that the constant current is flowing in the MOSFET, and thereby making the MOSFET behave as a linear element or almost linear element, something similar to the resistor. Now this is how the equation has been plotted. Now this is the equation of the MOSFET with respect to voltage and current, and this is the overlapped version wherein I'm showing the resistors graph as well as the enhancement load or the MOSFET's graph. Now in both the cases I can sense that they both have I is equal to 0 when we have V equal to 0, which means they both have increasing current with increasing voltage. So if not 100% but to the maximum extent, I can say that my enhancement load behaves almost like a resistor. So the moment you see a circuit like this wherein a resistor is being used as a load, I can immediately remove this resistor and replace this resistor with a MOSFET like this. Or to be very specific, I can replace this resistor with any MOSFET which has constant current flowing in it. Basically, I want to ensure that constant current is being pushed into the input device. Remember, this is the input device. Input device is the one where you are giving the input. So to the input device, the current to be pushed should be constant, and that can be achieved either through resistance or an element which is resembling almost like a resistance, which in this case is the MOSFET. So this is how I can replace my resistor with an enhancement load MOSFET. Now again, if I do that and if I can plot the graph, it will be resembling exactly the same way that it was behaving when I was using a discrete resistor. Now what is the small signal behavior of an enhancement load? Because we normally have discussed if I use a resistor and how does like for example, if I consider an example of common source amplifier, and common source amplifier was having a resistive load, and we have seen how that resistance was being considered while deriving the equation of the gain. Now since I am replacing that resistor and I am using an enhancement load MOSFET, what will be the small signal behavior of an enhancement load? Now to do that, so let's try to get into this structure over here. Like basically what we do, so here I have the load which is being connected in this fashion. Now I need to be determining the GM and R0 first. Now how do I determine GM? By using this formula 2K. Basically this 2K also stands for K n dash W by L. This is VGS minus VT, and I'll be also finding the finite output resistance R0, which is the impact of the channel length modulation. Now once I find that, I'll be replacing or I'll be inserting the MOSFET small signal model, which means I'm getting something like this. So basically this is my load. This load has a constant current being flowing over here, so and that can be modeled this way: GM times VGS multiplied by R0, which is connected between gate, source and drain. And if I want to redraw the circuit, it will look something like this. So this is how I'm going to get the small signal model for that particular circuit. Now if I simplify this further, so this is what I'm going to get. Basically you can see over here, I'm going to get a current is flowing from drain terminal to the source terminal, and just look over here, the current is flowing from the drain to the source, and gate and drain are being shorted. So that means the gate and drain, which was open over here in my previous all the normal MOSFET cases, now they are being shorted. So that's the reason we are shorting gate and drain, and the current is flowing from drain to source. Now if I just simplify this and if I rewrite this equation, it is going to resemble like this. So which means it all boils down to one point, which means the enhancement load MOSFET is behaving like a simple current source with an internal resistance, and that internal resistance can be written in the form of small R0. So this is how I can model my enhancement load MOSFET. So far we would have seen common source amplifier structure, something like this. So we require a bias voltage VB along with the small signal voltage Vs. Now we have a resistance R and the output is taken at the drain terminal, that is your DC voltage VD. We have VDD connected over here. Now this DC voltage is also having a small signal AC voltage also, that is capital V0 and small v0. We have I flowing through the MOSFET, that is ID. We are interested in the output voltage, that is DC output voltage, that is VDD minus I0 into R. Now the gain of the amplifier is given by V0 upon Vs is equal to minus Gm times Rd. Now I can increase the gain by two ways. One, so basically we want to increase this gain. So how can we increase the gain? So we want to increase the gain V0 upon Vs. Now there are two ways as such to increase this gain. Now one of the way is either to increase Gm or to increase R. Now if I increase Gm, this comes at the cost of, like, how can I do this by increasing the Gm? I can increase the Gm by increasing the drain current ID. So but by doing this, the overall power consumption, it also increases along with this. The other way to increase the gain is to increase the W by L ratio. So since W by L is directly related to Gm, so I can increase W by L. But if I increase W by L, definitely the capacitance also increases. And moreover, the bandwidth will have a decreased impact. And I don't want this to happen. I want my bandwidth to remain constant. Now the other way to increase the gain is to increase the resistance. So I can increase this resistance to increase the gain. And if I do this, if I increase the resistance, look here, if I increase the resistance, it will directly affect the output voltage, that is DC output voltage. So it will reduce the DC output voltage. Now I cannot directly increase R as per my wish. Now once V0 increases, V0 reduces, then this will make sure, or this will makes my M1 transistor move closer to the triode region from the saturation region, which means my MOSFET will start shifting from saturation region to triode region, which is again a bad symbol for amplification. I don't want this to happen because I want this particular transistor M1, let's say M1, to be remaining in the saturation region always to ensure proper amplification. And because of these all things happening, adverse effect, my MOSFET is getting shifted closely to the triode region, and that is a deviating condition from the amplification point of view. So which means to increase the gain, I can increase Gm, but that will have an adverse effect on ID. And I can increase Gm. How I can increase Gm? I can increase ID, or I can increase W by L, but that will have an adverse effect in terms of power and capacitance and bandwidth. I can increase the gain by increasing R, but that will have again adverse effect in terms of output voltage, thereby moving the transistor to the triode region.
So here goes the outline of today's lecture. Basically, in the today's lecture, we saw how the active load it will benefit the MOS amplifier and will play a vital role in the improvisation of the gain, and which will outperform the resistive load or any passive load devices. Now, in order to increase the gain of the MOS amplifier, since resistive load or any passive load is a very costly offense and it cannot be even fabricated on the ICs, hence we need an alternative to it, and which can be done, or which does the job role of the resistance, but not the resistance itself. So in that scenario, we figured out the alternative to the resistance or alternative to passive loads, and we found out that the current sources are the better alternative for the resistive loads. Remember, resistive load devices are will be ensuring a constant current, that will be a constant current flow through them, and the same constant current flowing nature can be obtained using current sources also, and that current sources are built using MOSFETs only, and hence we could see that MOS current source would become an appropriate choice for the MOS amplifiers when it comes to the load, and hence we go for an active load. So that was the summary of today's lecture. Thank you for the patience listening. We will see in the next lecture. Thank you.